Can anyone else? Oh, yes, excellent. Hello.
Yay!
Oh, hi. Hi. Oh, that's good. Excellent. It's always worry when there's a pause. Good. Welcome, everybody. It's really nice to see everybody from around the world again. So this is our third session that we've run today, and it's been, well, I hope you enjoy it as much as I've enjoyed the sessions earlier on. So Debbie has very kindly giving us a presentation today on STEM. Debbie is a prolific author and very experienced and knowledgeable teacher and trainer for primary and secondary science. And I think you're in for a really good, exciting and a bit of hands-on session. So I hope you enjoy it. Can I just, before we start, say that you will receive a certificate, a copy of the presentation, and also a recording of this presentation. It'll come out to you by the end of this week, so not exactly at the end of this presentation, but by the end of the week you will get this. And then the other thing to say is, if you have any questions as we're going through, please put them in the chat box. If we don't get to them, then don't worry, we'll pick them up later and we'll try to get a reply to you in the email that goes out following this presentation. So thank you again very much for joining us this afternoon, or this afternoon our time. For some of you, you've not actually got to the afternoon yet. Thank you, Debbie. I'll hand over to you.
Hello, everyone. Thanks so much for giving up your incredibly valuable time to be with us. Ideally, we'd be with you and we'd be in a room together and we'd be interacting, but you know, we're very lucky that we've got this opportunity, that at least we can share good practice. We teachers and educators together can work together and share this way. It's better, it's the best that it can be at the moment in time. So I'm really pleased to be with you. I love these sessions. I learn a lot from you people, and I hope that you'll learn a lot from today and build your confidence and become very efficient STEM practitioners. Some of you are already using STEM in the classroom, and so you're quite experienced. Some of you will want to work a little bit more and gain a little bit more confidence and maybe some ideas. So I'll go through some things first that for some of you, you might think, you know, if you're experienced. So let's just look at that as a refresher. And for the rest of us, let's look at this as an introduction or a building on opportunity for STEM. So I hope you can see this PowerPoint display okay. It's looking a bit weird on mine at the moment, but I'm loath to touch anything because I don't want to tempt fate. So we'll just keep it as it is. So as in any good lesson and in a good training session, it's just the same. We will look at the objectives for this session. It is a objective led, as STEM learning should be. So we're looking at STEM really for the primary classroom, but obviously we should really be starting to train our students in STEM as soon as they start school, in early years, in kindergarten, in nursery, whatever you want to call it, preschool. We're having a look at how to implement STEM in the primary classroom. So for you practitioners out there, so that you can actually plan and design ideas to implement STEM successfully. We'll also look at how STEM is cross-curricular and look at some ideas that will incorporate that. And my main message is, because I'm a physics specialist and I've also taught maths and science are actually fun. A lot of times I get students telling me that I don't like maths, I don't like science because it's difficult. And I say, how do you know it's difficult? Because my brother, my mum, my dad, my sister, my next door neighbour, someone somewhere once has told them that maths and science isn't fun. It's actually very difficult. Well, that's not actually true, because maths and science explains everything around us. And our main focus as educators is to help students to explain the world around them and be able to behave in it responsibly. So the key points are that science, technology, engineering and mathematics in the primary classroom will look at how to plan lessons, to incorporate STEM into primary learning and teaching, to gain confidence in what STEM actually means in the primary setting, and to look at some STEM activities to provide some hands-on, minds-on opportunities. Students really enjoy STEM lessons. I'm told this by students, I'm told this by practitioners, I'm told this by people who actually work in the STEM field. We enjoy STEM. It is hands-on. It's okay to get your hands dirty. It's okay to mess things up a little bit, because that's how we learn in STEM lessons. So in the primary classroom, science, technology, engineering and mathematics, and sometimes art. So sometimes it's called STEAM. I prefer to stick to STEM because I think we incorporate art anyway by looking at diagrams, by drawing diagrams, by looking at pictures, video clips. We are immersed in art anyway. So we're focusing on science, technology, engineering and maths for this. So hello to everyone who's joining us, and welcome. You haven't missed anything. We're just introducing things at the moment. So this STEM has a profound impact on everyday lives. So it's around us all the time. It's impacting on everyday life. Yet students haven't always pursued them as extra subjects, as a specific subject. Lots of educators, particularly people who are responsible for the curriculum in schools, ask me certain questions, and they are: do we have to write a separate curriculum for STEM? Do we need to invest this time so that we can actually teach STEM in school? The answer to that is not easy. You don't have to write a STEM curriculum. You can incorporate STEM lessons into all lessons across the curriculum. You can identify them as specific STEM lessons, or you can identify the aspects of STEM that you're actually teaching in a pre-designed lesson. I hope that makes sense. You could teach one-off STEM lessons. These could be a specific STEM lesson. Often schools introduce into their curriculum STEM as an extra day. It could be an after-school event, a STEM club, an introduction to the STEM technique as a one-off lesson. So sometimes they're taught alongside and they're just identified as STEM lessons, but often in the early stages they are specific. This is a STEM lesson. Today we will be learning about STEM. So it's not a straightforward answer, but as long as you're teaching STEM and you're conscious of what counts as science, technology, engineering or maths, then you're teaching STEM, and that's a good starting point. So STEM learning teaches children more than just key concepts and content. It actually teaches and develops skills. And we'll look at these skills in a little bit more detail in a minute. The focus is hands-on learning, but with real life, real world applications. When I'm observing lessons, I'm always amazed how teachers will teach a great lesson, and I ask the children, what is your experience of this? And often I'm told, I don't know, I don't really know. We have to make sure that it's linked to things that they understand and experiences that they might have or may well witness. So we need to be very careful that we link it to the real world around our students. So we're developing skills and we're encouraging creativity. These aspects are often not linked to science, technology, engineering or maths. They are often linked to the humanities, to creativity is linked to designing or in art, things like that. But actually we're encouraging it in science and mathematics. So my key message from the experience that I've got, my own experience starting to teach STEM in a classroom, my experience in training people and training teacher trainers to train teachers to deliver STEM lessons. This is based on my experience, and your experience might be different, but these are my ideas. Use the resources that you have. This is really important because what we want to encourage in STEM lessons is that children feel very comfortable and that they are very knowledgeable, that they are not making a mistake. It isn't a mistake. We're not making errors. We're not getting results that we might expect. Things might turn out slightly different than we thought they would do. Now, as scientists, if we were working on something, on a project, an investigation, or a test, or a method, and we got a result that wasn't exactly what we predicted, our hypotheses didn't actually incorporate the result that we're looking at, what would we do as scientists? We'd repeat it. We'd do it again. We'd make sure that we'd not made a mistake. Humans make mistakes. We would make sure that we'd done everything that we could to get the result. We'd repeat it. Often I'm observing lessons and the teacher will say, there's one each. You've only got one chance to get this right. There's one between four. We've got one of these resources between six. So you must get it right. Well, if that's the case, don't do it. If you've only got one resource for a child or a group of children, don't do it. Do something alternate, because we want them to be comfortable in repeating things. And if it's too expensive to repeat, then they're missing the whole point of doing the investigation. Tweak what you have. Look at your lesson plans. Do I actually need to write a STEM lesson plan? Or could I actually incorporate STEM into this lesson that I've already designed and that already works and I've already got the resources for? Do that first. Use materials that are available. Design lessons and plan lessons using the materials that you know you can find. That's what I've done today. And I'll share these ideas with you. I'm in lockdown. I can't go to the shop. I can't go into school. I can't go into my schools and take from the shelf the resources that I need. I've had to use what's here in my house. Now, luckily, I am a scientist and an engineer, and so I have got lots of things around the house, as we teachers do. We often have lots of things at home. Someone once told me teachers are different. Most people who work in the workplace take something home from the workplace. It could be a pen or a piece of paper. Teachers take things from home into the workplace. How often are we leaving home and we've got bags full of equipment and things that we've taken from our cupboards? So I'm lucky that I'm a teacher. I have got quite a few resources, but I've had to be creative for this practical session. So you don't have to spend money. And if it doesn't go to plan, use it as a learning opportunity. Celebrate it. This is a great opportunity to learn how to put things right, to accept that things might not turn out the way that we want them to, and be comfortable that, because STEM is trial and error. That's what it is. That's the key ethos behind STEM. It's trial and error. Now, the research tells us that the importance of STEM in education, and particularly in primary education, are these. This is taken directly from research. It promotes ingenuity and creativity. It actually celebrates creativity in the classroom. Children and students are encouraged to develop new ideas, because as they grow into scientists and technologists and engineers, they will become the innovators of our future world. And it's our responsibility to encourage them to develop these new ideas and be resilient. If things don't turn out how they think they should, keep on going. Keep going, and be resilient. It's a key skill, not just for STEM, but for life. It encourages teamwork and team events, whether you might be the team leader, you might be the project manager, or you might be a team player. This is life. This is preparing our students for the next stage in their education and in their life. Playing a part in a team and knowing your role in that team makes the team successful as a whole. It's not about me, it's about us as a team. And this is a skill that STEM really, really, really pushes to the forefront. It teaches children to apply the knowledge. Now, we know that students who succeed to a higher level in education are capable and confident of actually applying knowledge to new and unusual situations. So, how many times in an interview at university? Something very odd is happening to my computer today. I hope that doesn't affect you. So, sorry about that. So when you go for an interview or a higher level opportunity at a university or something like that, how many times are we asked a question and we walk away and think, but we've not done that, we've not covered that? And that's because it's a skill, it's a high level skill to be able to synthesize the knowledge that you've gained into completely new situations. It builds confidence in technology. Technology is a big part, it's a big umbrella in STEM learning. It teaches problem solving. Students are confident in thinking, yeah, that's pretty difficult. I'm not 100% certain, but I think, and I will try that. And if it doesn't work, well, it doesn't matter. I've not lost anything. I'll try something else. They can adapt themselves to new situations, and it promotes analytical thinking. Analytical thinking skills. My son said to me a long time ago, I went to buy a car and I was looking at it and thinking, the insurance will be this much. It'll cost me this much to look at to actually maintain it. He said, and I thought that's something you taught me. And I actually taught him that in a science lesson. But he said he used it as an adult, being able to weigh things up, problem solve it, and analytically think about all the facts that were placed before him when he bought his car. Okay, so STEM in science. I'm going to break it up into science, technology, engineering, and maths, which for some of you who are extremely proficient in STEM, it will be a refresher because often we forget, and lots of teachers ask me specifically about engineering. I find it difficult to incorporate engineering into a lesson, but you'll see from this session that you're already doing it. You just might not recognize that that's an engineering skill. So I hope you don't mind me just unpicking this briefly, just so that we're all in the same position. We're all confident that we know what STEM actually means and what it looks like in the primary classroom. So in science, we're exploring the world around us. We're making sense of everything around us. Why is there a cloud in the sky? What is a cloud? Is it really a ball of fluff? No, it's not. Asking questions. Asking questions is at the centre of inquiry-based learning. Notice I don't say science inquiry. Notice I say inquiry-based learning. Inquiry-based learning should be taught in all lessons, not just science. But the questioning is at the heart of inquiry-based learning. It's at the heart of hands-on learning. If your students walk into your classroom and say, why? Why is that happening? Why does that work like that? Then already they're engaged and they're in control of their own learning because they want to find the answer to the question that they've just posed, and which means that you've already got them engrossed in the learning. They learn to plan. They learn about methodology, about sequencing and common sense approaches to problems. They learn to observe and measure, accurately, and to record in detail and accurately, to record in a way that they can share their results so others can actually test the results, because the more results we get, the more reliable and the more repeatable the investigation is. They learn to draw conclusions. They learn research skills. They learn how to research effectively and what research to use and what research to not use. They learn scientific systems, including cause and effect. And that's the science part of STEM. The technology bit is a huge umbrella, and it's an umbrella term that encompasses a number of different things. Communication and information. I've observed some students who really are challenged in the classroom, who really find it difficult to sit and to apply themselves. And yet, when we sit them in front of a laptop or a computer, their attitude changes completely because they know that they're successful and that they can communicate effectively and at the same level as everyone else when they're using technology. The use of technological tools. So we're thinking about, things like light gates. We're thinking about a pH detector, a noise level detector, rather than old-fashioned traditional methods of measuring. So we're also talking about enhanced learning, teaching and assessment, because using technology means that we have instant feedback and we can have instant information from the students as they work. It's computer-based learning, which encompasses blended learning techniques. Blended learning techniques are huge now, and it is mainly because of COVID. Lots of people, lots of teachers have found themselves in situations where they're being expected to actually educate children in a completely different setting. I observed a lesson recently where the teacher was at home on a platform like this, teaching a class of 30. And they were all looking at the interactive board, just like you're looking at your screens now. And that worked. And that meant that this A level, this higher level class, wasn't missing out on valuable teaching and learning. We're using multimedia tools. We can say that it's supplementing learning, it's adding, it's additional, it's a different kind of learning. It encourages critical thinking. Why is this not working? Why won't this mouse work like I want it to? Why can't I build this table? Why doesn't it look right? So it encourages all that kind of thinking and that problem solving. It gives confidence, and children tell us that they feel comfortable using technology. And I know this is true because I watch young children and they can use a smartphone like that. Their smartphone skills are impeccable. They can sit on a computer or a laptop and do things that it would take me ages because they're quick, the thinking is quick, and they're used to it and they enjoy it. So therefore they're successful. It's engaging, it's stimulating, and hopefully, if we've got the hardware, it's accessible. Students can access the information confidently and competently. Engineering, the bit where some people tell me, I'm not really sure where engineering fits into my lessons. I don't really plan the engineering aspect. Well, the engineering encompasses the following. Design. How many times do you ask your children to design something? Often. It produces and gives us solutions for real world problems. That's what engineering is. It helps us to apply and synthesize the knowledge that we've already got, the knowledge that we get from science and maths. It helps us to apply that knowledge to new situations and to problems. It gives us the technology and the expertise to develop machines that will support us, make things quicker, easier, change forces, change the direction of the force, change the amount of force that's needed. Engineering helps us to process information and to process equipment, machinery quickly and efficiently. It develops systems that we can use that are effective and they manage time effectively and it also gives us the creativity to make these new innovations that we're so interested in. And then the maths aspect. The means and the foundation to the solid development of the skills of learning, logical thinking and reasoning. That's the definition of mathematics in primary education. It develops skills, and these skills, are you noticing that they're cross-curricular? These skills are in science, technology, engineering, maths, art, English, the whole of the curriculum. We can make designs, we can draw designs and effective and accurate designs. It's challenging and we can challenge others, we can problem solve. Importantly, children learn to be confident and competent with number and quantity. They have a spatial awareness, and they understand and relay and link and identify patterns in data. It's strongly linked to science. I've always taught maths, and for me, maths is science. Science is maths. And way back, maths used to be described as the science of maths. And so science and maths are hand in hand, always have been, always now will be, because of STEM. It helps children to communicate in a complex, often complex language that's only used in maths, a complex language that's only used in science. And how do they learn this complex language? From us. Where on earth do you think children will hear things like volume, capacity, square root, no, centimetre cubed? Where are they going to hear that? The only place they're going to hear it is from us. And we have to model that language, and we have to be confident and competent in using that language, especially for children who speak English and are learning STEM in English as an additional language. Where else are they going to get that experience? From us. And to get to a higher level in education, we need to model pronunciation so that children can also pronounce it correctly. And that helps often with the spelling, and it helps with the use. The more confident they are in verbalizing complex vocabulary, the more confident they are in using it in the written form. Students learn to collaborate and share. They learn to work with others, and they learn critical thinking. Critical thinking is really valuable in STEM education. Let's get cracking. Let's start to look at some practicals that I've put together for you. Now, isn't this exciting? Okay, so I'm grounded. I'm stuck in my office. Look how tiny it is. I'm used to having big laboratories with lots of equipment, and a technician will run around and find me everything I need. But when I've been doing these webinars, I have become much more creative. Okay, I had some school glue. I did. I also had some baking soda. I had some iron oxide, which is a little bit worrying that at home I would have iron filings. Of course, everyone's got iron filings in their kitchen cupboard. These actually I bought online because I knew I'd be needing them for various different things. And in UK sterling, these were £2. So if you want to do a conversion, and I've done 3 or 4 of these webinars, and I've not even used a quarter, I wouldn't say. So that one is a really cost-effective thing to buy. Now, I didn't have any borax, so I thought I'll use contact lens solution. That works really well. Unfortunately, my son, who I used to borrow contact lens solution from, doesn't use the solution anymore. So I had to be a little bit creative. So I thought, do you know what? I'll try and use something else and pass this on to you if it works. And if it doesn't work, you might be able to pick this up and you might be able to make it work. And when you do, it'll be a cheap alternative to using borax or contact lens solution, glue, baking soda. So what I did actually use, I used dish soap. Any dish soap will do. It doesn't really matter. I've tried this with a couple. Both work the same. I would, if I was you, get the cheapest one that you possibly can and try that first. And so what I did was I put into the bottom, I look like a TV chef, don't I, using these little pots. I was trying to use something, so that you could see what I was actually doing. You might want to get the children to do this because it's quite time consuming, and I imagine making a big batch of it would be quite time consuming. But I guess that you would just have to allow the time to make it, basically. So what I did was I put into the bottom of my little dish enough dish soap to make as much volume of slime as I wanted. So I put that in the bottom, and I added salt. And then what you have to do is, because as you can see, that looks very different to the dish soap. It's actually a different consistency, and it's actually a different colour as well. What you've got to do is you've got to get as much air in there as you possibly can. You've got to get air bubbles in the dish soap, and so it does take quite a lot of stirring. And then, because you know how imaginative and creative we are in STEM, I thought that's not really the right consistency. So I also tried to put it in the freezer, and that actually did help rather a lot. But this has now been out of the freezer quite a long time, and so the consistency's changed slightly, but it actually isn't that far off, and it's cost me virtually nothing. I then mixed in a very small amount of the iron filings. On here it says iron oxide powder. If you use an iron oxide powder, don't forget that it can be toxic. It is toxic if you inhale it, specifically if you inhale it. If you get it in your eyes, so I would suggest if you are using it to wear goggles. And I'd also use gloves actually, because if you get it down your fingernail or anything like that, you just don't want to ingest it in any way, shape or form. But it works. Iron filings are slightly better to use because it's not a powder. It's a bit harder to ingest. It then says to use a neodymium, you know, the little tiny magnets, the ones that you have on fridge magnets and things like that. I just didn't have any. So that's that. I just haven't got any. But what I have got is a traditional bar magnet. And I hope you can see that it does attract it. Now, if you're using a bar magnet or another kind of magnet, just this one's wrapped in sellotape. Cover it in cling film or wrap it in sellotape, and then when you finish, when the children have finished, just take off the tape or the covering and throw it away. You'll never get that clean. It'll take absolutely ages. I also tried this recipe. This one is hand soap. It's just hand gel, and that's mixed with salt, and I put a little bit of baking soda in there. This one I don't think is quite as successful, but it does work, and with the small magnet you can attract it. Now what's the point? How are you going to use that in science? I told you, don't do an investigation unless it means something to the children. So what would be the point of doing this investigation? Well, we can talk about making mixtures. We can talk about changes of state. We can also say you could give the children this, and if you put black food colouring in it, you can't see the iron filings. And so you could say to them, okay, here you are, you've got a mixture. I want you to find the properties of it. They could work in teams, and they could have a role in that team, a project manager or whatever, and plan a method to find out the properties of this. They could try stretching it. They could use a syringe and try to compress it. Does it compress? So they could put some in there and try and squash it together. They can try and stretch it. You could give them a magnet, and hey ho, they would then be surprised that it's magnetic. So then they would have to figure out why it's magnetic, and hopefully they'd find that they've got a magnetic material in there, which is iron. While we're talking about magnets, is it possible to break a magnet? Yes, it is. It is. And most children tell me, no, you cannot break a magnet. One said, look, miss, it's really hard. How would you break this? Well, a magnet is only a magnet because it's a magnetic material where all the domains are all lined up facing the same pole. If you continually drop your magnet, the poles are all over the place and it's no longer a magnet, it's a magnetic material. And so, yes, you can break a magnet. The way to stop children dropping magnets is to ask them to remagnetize them one lunchtime. It's very boring, stroking a magnet with another magnet until it becomes magnetic again. And you never forget that how easy it is to break a magnet. I only did that in secondary science, honestly. Okay, here's my oil spill. Again, I'm working from home, so I've got a miniature sea there or ocean. Can you see all the grease and grime and yuck on the top? I haven't got any model fish. I haven't coloured it blue, but you could colour the water blue, and then colour the oil green or black or brown, make it look really, you could put some dirt, mud, charcoal, anything in there to make it look like polluted water. You can use things that are on the screen, because that's a free resource from STEM. So there are lots of different free resources that you can use. But for me, because it's about STEM, I would want it to be linked to something that the children are familiar with. So has there been an oil spill recently? Has one been in the news? Has there been an oil spill that was near where you are, the country where you are? Has there been, will their parents, grandparents or something remember a massive oil spill that's more meaningful to them? And then you could set it as a competition. You could say, okay, your job is to clean up this oil spill. They can make more of an oil spill. I use these all of the time because I get them free from a local chemist. If the wrapping is broken, they're no longer sterile, and so they give them to me so that I can share them with local schools, and we use them for all sorts of things. Because it's free basically. But you can get them to make their oil spill by actually dropping more oil, dropping it onto the surface of the water, and let them explore how the oil forms little droplets of oil on the surface of the water, and talk about the density and why doesn't it flow, and why is it. You could even go into the hydrophilic molecules on the ends of the detergent and things like that, and that's how it breaks it up. And then they might choose to use detergent, so they'll drop the detergent onto the surface of the water and observe what impact that has on the oil spill, because this is what's done in a large scale. This is how an oil spill is cleaned up in reality. And so all we're doing is micro scale, and we need to make sure we keep telling them that. Notice how, we're doing some of these investigations, but it's the way that you put it across. This is a micro scale. This is what happens in the real world. This is what happens in nature. This is what happens in the ocean, and this is how it's cleaned up. Which method is most effective? So some students might want to choose a cotton wool pad. If you float this on the surface of the water, it will float, and it will pick up as it floats across the surface. It will pick up the oil spill, dispose of that, and you will eventually get rid of the oil that's on the surface of the water. This one's a little bit more time consuming. You can actually use a cotton bud, and if you sort of twirl it on the oil spill, it again will pick up the oil, but it is time consuming, so we need to be conscious of that. You need to plan that into your lesson, don't you, how much time you've got, and so therefore how much you can go. But the whole point is that this is what happens in the real world. This is not just science. This is not so that you can pass a science assessment. This is because this is happening all the time around the globe. I really like these because we said in maths it's really important that children are very confident in number, that it's not intimidating, and that they actually are competent enough to look how young that child is. So I like these. I'd like to write on sticky notes numbers, stick them around, and then we could have a student choose a number, or you could use the number that's that you're teaching at the moment, the level that the students are at, and ask them. In this case on the slide it says what makes 10. So let's see if we can make 10 from our sticky notes, shall we? So the first number we've got is 1. So what number do we need to come next? 9. Oh, look, just so happens to be a number 9. So 9 plus 1 makes 10. Oh, look, it's like a miracle. An 8 plus 2 makes 10. I'm sure I didn't do that on purpose. I'm sure you will be more creative. But there's the idea. So that could just be an activity where students are allowed to just go up to the board and actually make up their number sequences using the sticky notes. And they enjoy it because, let's be fair, everyone enjoys using a sticky note because it's not permanent. Which means that if you make a mistake, it doesn't matter. You can just change the sticky notes around. It's not a permanent thing. And that is a really powerful learning tool for children, because it's they are confident to have a go because they know that they can change it. They won't be assessed or judged on what they've done because it's not permanent. So they can change it, and in changing it, they're actually learning. I've included this, and it's difficult for me because I am not promoting Lego in any way, shape, or form. What I want to show you is that in teaching technology, using some resources that can be extremely expensive, as these are, you can actually miss the learning intention by not fully understanding. Okay, so I just wanted to share this with you, and I'm sure you'll all go, oh yeah, I knew that. Well, that's great. But I also teach computing and computer programming, and often when I'm supporting teachers, I observe a great lesson, and I think you just missed it by a tiny amount. And so I just wanted to reinforce this. If you look at the picture on the rug with the big chunky Lego, that's actually one of my lessons. Okay, so as soon as you get Lego out, doesn't matter how old people are, I use these when I'm teaching computer programming to adults who are often teacher trainers. So the very high level people, as soon as I get the Lego out, they're in there, they're enjoying it, they're engaged, they're loving it. So for example, this made me laugh today because the last time I used this was with trainee teachers. And when we put it all away, not all of it was put away properly or taken apart, shall we say. And so I got this out of the box to show you today. And look at this. This is teacher trainers, bear in mind. They've used this. Look inside. They've even put a pilot in there and a passenger. So that's how creative, imaginative. That's what happens when we use Lego. Even though we're grown-ups, it all becomes great fun. Now, I observed this lesson and the students loved it. Everyone was laughing, smiling, totally enjoying watching the trains going round the track, because the Lego trains, they toot, they have smoke coming. It's fantastic. And afterwards, I said to some of the children, so what were you doing? We were playing with Lego. Okay, and so what was special about the Lego train, or well, it was a train in this case, it went round the track, and that was it. Now, what is special about this? This is about computer programming. If you look at the track, you'll see that there's a little red block like this white one. Each of the blocks in Lego programming actually gives an instruction to the Lego processor, and the processor's in the bottom. So as the processor goes over that block, it instructs the processor to do something. So for example, the red one tells the train, or whatever it is, the vehicle that they've made, it tells it to stop. It's an emergency stop. It tells it to stop. This one tells it to refuel. So it stops, and you can hear it going doo, doo, doo as the fuel's going into the train. The blue one tells it to do something completely different. I think it stops at the station and picks people up. So when you're teaching it, you should be saying, you've put the red block in. What if you change the red block for the blue block? Oh, the train will fuel. What if? Because what if is computer language. So it's actually training the children to make the link between what if the train will do something different. Does that make sense? So quite simply, by working with the students and saying, this is coding, okay? You're coding, you're telling that train, that plane to do something. And it's by the sequence of the blocks that you're telling the train how to do it. So can you see that this is very expensive resource? It's a very expensive resource. The children enjoyed it. but they didn't learn anything about programming. And the point of it is that we're teaching programming, because now in all curriculum around the world, children have to learn complex programming that disappeared from the curriculum for a long time. Why? Because they're expected. They're expected to understand how a computer works on a very complex level, because that's what they'll be expected to do, because computers are incredibly important. Oh, thanks, Evelyn, for sharing that one of your students did this same coding. That's great. At the Lego, science exhibition. So that's the kind of thing I do. So like it's fantastic, even if it's used well. The one at the side is the next one up. That's the one where they're actually using a laptop or a tablet to actually physically drag and drop information into sequence, and if they don't get the sequence right, it won't work. And so it's really, really giving you a fantastic introduction to sequencing and programming, which is great. Okay, I would apologise for this jug. This is my science jug. It goes all over the place with me. Can you see how disgusting it is? The reason I keep this one just for science is because I used to use things for science and then put it away in my cupboard, and my family were quite disgusted by it, because often I'd be catching soil invertebrate and things and then using it to make a sauce or something. So I just keep this one for this now. Now all day this has been making me cough, okay, because there I go. Okay, so I've given you this ratio to use. This is a crystal sun catcher. Now I've made this with grown-ups, children of all ages, and they absolutely love making these. Okay, so the best way to do it is a 1-to-1 ratio with water, and I used Epsom salts because it generally makes a better crystal. But you can use any salt at all. But you need a very, very, very concentrated solution. Okay, it needs to be saturated, and that's why I showed you that. If you can see, I don't know if you can see very clearly, but if you can see round about sort of here, you can see where the Epsom salt, the salt is actually crystallizing on the side as the water just at room temperature has been evaporating throughout the day. So that's how concentrated it is. It's really, really saturated, so you can't get any more in. That one has got a lavender perfume in it, and that's why I'm coughing, because it's so concentrated. The lavender is really, really strong. It's not relaxing and putting me to sleep, it's just making me cough. Now, the ideal way to do it, this is a clear lid from a yogurt pot. So just collect rubbish. You know, I said to you in STEM, you don't need to actually use anything expensive. I just collect things. You'll see as we go along that I just collect rubbish, really. I see something and think, oh, that'd be great. I'm going to use that one day, and there you go. So this is just from a yogurt pot. So the ideal way to do it is the slower the crystals form, the slower the water evaporates, the bigger and better the crystals are. Okay, and then wind, breeze, warm breeze is great. In the UK at the moment, no warm breeze. So I've done this next to a radiator, and it's evaporated a little bit too quick, and it's left the crystals quite crumbly. So tricks of the trade are slower the better, very concentrated, and make sure that the lid is really clean. If there's any grease or oil on there, it will stop the water evaporating, and you'll just get a mushy mess. This isn't perfect, but I still love it. So one of those crystals is going to fall off any second. Can you see how it's catching the light? So how much STEM have we got in here? Right, well, we've got science. We've made a solution from a solvent and a solute. We've used the universal solute, water. We've talked about the salt can't have disappeared when it's dissolved. It must still be in the water, otherwise we wouldn't get the crystals, would we? We've talked about a very saturated solution. We've talked about evaporation. We've actually engineered a new product. We've made something. We've talked about ratio 1-to-1 in maths. We could talk about technology, and we could actually research sun catchers. I like to thread an elastic band through these, and so it bounces, because if you hang it, I'm trying to get the light for you, but now the light's above me because it's dark in the UK now. But I'm sure you get the idea of it. Children and anyone really enjoy making these, I must say. But if you put it on an elastic band, put it on a window catch, a nice sunny window, as it bounces in the sun, it reflects and it refracts the light. So how much STEM have we talked about making something? We had a open event, and the children mixed different colours. They really explored different salts, different colours, different ways of making the crystals bigger, and they displayed them on strings and elastic bands in trees and around the school. And it was a sunny day, and it reflected the light, and the children really enjoyed it. And yet look how much STEM we've got in there. Do you see what I was saying at the beginning, where we don't have to plan particular STEM lessons? We've actually got everything here. This one's really important. We've got a world food shortage, and a lot of the world is, because of global warming, underwater. Look at all the things from my trash, the things that I collect that I told you about. So 2 bottles taped to the bottom of a container that had grapes in it. We've got soil in there, and we've got grass growing. And you'll just have to trust me on this, because I'm not bringing a water trough in here in front of my computer, because then I'll never be able to do another webinar again, and we'll miss each other, won't we? So you'll just have to take my word for it. This does float, and this has got a lot of soil in there, enough to grow grass. Okay, so this is a great STEM activity, because you could just give them a box of recycled materials that are nice and clean, explain, it could be after a lesson about global warming or something like that, rising sea levels, talk about world food shortage. It could be incorporated at any point, but notice how we're linking it to the real world. It's not just an add-on activity, it's actually linked to something we've been learning about in the real world. Look what we need there. Nothing. This has cost absolutely nothing, but hopefully it's made children realise that we can grow food still, even if it's flooded, even if we're waterlogged. Oh yeah, this is a good one. I made one of these earlier. Okay, so here we are. Plastic coat hanger. Various different ways of doing this, but I always do it this way because the children can actually hold onto the top and they can see the balance. Now, the important thing is that the strings are the same length. That's your important thing, so it's balanced. And then rather than just using a scale or a top pan balance, the students can actually understand about balancing. We can introduce mass, weight, volume. We can introduce moments. We can start talking about how to balance it out. In this side, I've got some pebbles, and in that side, I've got a golf ball. You could use anything. And to balance it out, we can use pebbles, coins, marbles. You could use proper scientific weights if you had them available. But again, the message is we want all the children to be able to get involved. So if you haven't got enough weights for everyone to be engrossed and involved, use pebbles, use coins, whatever you've got. It will work. They work great. The one on the PowerPoint slide, that's for the children who really enjoy construction and engineering. To be honest, I'm not very patient, and it is really easy to build that, and it does work. But I prefer the coat hanger because it's quick, easy. But it depends what your children are like. I mean, these wooden popsicle sticks, you can use recycled ones if you want to. But again, UK sterling, £1. They were about £1, I think. And I've used loads. There were loads in there. I've used them for all sorts of things. And that's just made out of recyclable things. Other than that, a plastic cotton bobbin, a few straws, yogurt pots or fruit pots. That's it. And a bit of string. So it costs nothing. But we could really let the children explore who can get the most accurate, which one works the best, that kind of thing. Oh, here we go. If anybody watched my recent webinar, this then was a Tolgram funnel. I love these. 1.5 litre, 2 litre bottles are absolutely amazing for all sorts of things. This week, this is not a Tulgrim funnel to collect soil invertebrate. This week, it's a filtration system. So on the bottom there, I've got some filter paper, which is a slight lie. I didn't have any filter paper, but I don't know if you're aware, if you use wipes, sorry about the colours, as you can see, it's from the magnet earlier. This is just a baby wipe that I've hung out and it's dried, and it's fantastic filter paper. Works immaculately. It works incredibly well. So that's what I've used on the bottom, just with an elastic band securing it in place. For my experiment, I've decided to use some pebbles and the filter paper. You will need some muddy water. There you go. Pour that in there and you'd be amazed how clean it comes out. The idea is that these students on the top picture have used lots of different techniques. They've worked together as a team and used different techniques to actually we say it's cleaned the water. It hasn't. It's filtered out the solid parts. That's it. Please, 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 even if it looks really clean, remind students that you might have taken out the solid pieces of dirt, dust, leaves, gravel, but there could still be microorganisms in there. So that's another discussion in STEM. What can we talk about? So on this one, we've got science again, we've got technology, and we've got engineering. We're constructing something and designing something, using our own ideas to do that. And we could incorporate maths. We could say how many times we've had to do it, how much water we got that was clean, how long it took, all this kind of thing. I'm rushing now because I'm running out of time. I'm not very good at time. Once I start doing practical events, I could stay here all day. That's the problem. Okay, the rubber band helicopter. I haven't actually made this for you today because I couldn't get the propellers. Sometimes you can buy them online, but I just couldn't. But this one's really good because they can design it. So they're doing the engineering part. They can talk about the science part and link it to how it's actually, why is it flying? How are you actually getting it to go against gravity, to have enough push to actually work, to actually fly? We can link it to seeds and how in nature seeds use a similar technique. We can talk about the transfer of energy from the elastic band, the twisted elastic band, how the energy is stored in the elastic band, and when it's released, it transforms into kinetic energy, which makes it move. We could measure it. We could ask the children to have a starting point, design an helicopter. Here's the equipment. Who can make their helicopter fly either the highest, the furthest? So we could have a starting point. We could then have markers to show where it landed, measure it, record the results, compare the results, and discuss the results, analyse the results. So again, great STEM activity. I've seen children loving this. I once did a STEM day at a museum, and the children all had to power an electrical circuit that would drive a car that they'd designed, and all they could use was a sweet potato. And you'd be amazed the distance some travelled, and you'd be amazed how fast they went. Unbelievable. From a sweet potato. One of my most favourite lessons, that actually. So again, so much STEM that can be taught from an activity the students really enjoy. They're really enjoying being in control and in charge of their own lesson. Using levers, a simple machine, one of the 6 simple machines, but then used in so many other machines, used in more complex or compound machines such as wheelbarrows or cranes or diggers or forklift trucks, used in so many different things, and yet we don't really study it or put it to pieces. So I gave my students lollipop sticks, elastic bands, and a bottle top. And they came up with what's in the picture. So what you've got here is just 2 lollipop sticks quite tightly joined together at either end. I've actually used you know, the lunchbox metal wrap things, like tie wraps. I've used things like that on them because they just last a little bit longer, really. But that's down to you. You know, you can explore and experiment. And then we've made the fulcrum by joining another two together. That was just a really tight elastic band on the end there. I hope you can see it. This is held in position just using modelling clay. So this is the launch part. So we can talk about the distance from the launch from the fulcrum. We can talk about the height of the lever. Would it work better if we move the fulcrum nearer to the launch, or would it work better if it was nearer the fulcrum? We can measure it. We can measure that, and we can measure the distance, and we can calculate it. So we're using maths. So we've used science because it's a lever, it's a simple machine. We've used technology because we can research it, all the different uses that we've just talked about, all the ways that machines are used in compound and complex machines. We've got engineering, we've actually designed it, we've constructed it. Maths, we're going to make measurements of it and we're going to measure the distance it goes. Can use this. Children are brilliant with these, they can make them go miles, like that one just did. That one just landed in the ocean, in the oil spill, so I'll clean that up later. This is a much better way of teaching levers because it's hands-on, it's minds-on, it's engaging. That's the thing. That's the beauty of it. So that draws us to the end of that. We could have gone on all day there. Thank you so much for your feedback. It's just phenomenal, the positivity. I always enjoy these sessions because I really do enjoy hands-on engaging kitchen science. I don't care how old people are. I just wish we were together. You would be flicking things all over the room now, wouldn't you? But any questions, if I can help you in any way at all, please do contact me. I do like hearing from teachers. It's a lonely life sat in this study talking to this computer. So thank you for your fantastic comments. Really appreciate it.
Thank you, Debbie, so much for yet another really engaging webinar. Thank you, everybody, for joining us, taking time out of your day to learn more about STEM. And I hope you feel really inspired by this and take away some good ideas here. Just to remind you that your certificate, the presentation, and a link to watch again will be sent to you by the end of the week. We are drawing to the end now of our webinars for autumn term 2020. So we are looking for ideas, topics that you'd like covered in 2021. Please email us on international.curriculum@macmillaneducation.com with any suggestions, and we'll do our very best to support you. Thank you again. Thanks, Debbie, very much indeed. Wherever you are, enjoy the rest of your day. Thank you. Goodbye,
Thank you.
everyone.
Bye.